Hey, so guys, I think, oh shoot, that didn't update. Sorry, just a second. I got to do this differently. There we go. So guys, this is where I'd like to start. For those of you that were in that bottom left-hand category that said, no, you have not mastered all the essentials and you got less than 85% on the test, you again are the people that are qualified to take advantage of this remediation process. Guys, this is what it looks like. I know that some of you have never done this before, so let's be clear. In order to engage in the process, there are 3 things that you've got to do before you engage with me and Miss Call. So what you need to do is click on, number 1, click on the link and watch the video and take notes. It's about 25 minutes long. All it covers is the essentials. Super focused. And then guys, number 2, you're going to print this assignment and you're going to do it. And then you're going to check your answers, number 3. When you're done with that, that will give you 2 things. It will give you an assignment that's done, and it will give you video notes. You will then bring those on January 18th or 20th to my room. Miss Call's kids will be in here. We remediate together. Then we'll reteach. We'll answer questions, Q&A. You'll get another assignment that you will take home. You'll do. You will then check your answers to that. And then, guys, that second assignment becomes your ticket to get into the Essentials test, which will be on January 21st. And, guys, they all look the same. The first assignment, the second assignment, and the test are all exactly, not the same questions, but the same structure. And by that point, people knock this out of the park. You get an 80% on the Essentials test, demonstrating mastery, and good things happen to your grade. So, guys, to put that in context, let's look at it on a calendar. So here's how it goes. This is where we are right now, and remediation isn't until not next week, but the week following. So you've got an entire amount of period in there to get that stuff done. You got a long time. And then remediation are these days next week, or the following week. So keep an eye on that. So guys, in addition to that, let's sort of get a sense of what we're up to. We are actually going to finally be back in lab. Guys, think about how long, when is the last time you were in lab? Dang, good job. Guys, that was it. The flame test lab. 2 units ago. It was like early October, and that's the last time you guys were in lab. It's not because we're not doing labs, right? It's just because the labs are like the cut and paste lab, and it's like the model kit lab. It's been a long time since we are in lab. Guys, that's not the case for the rest of the year. We're in lab a lot and ever increasing. So here's how this unit goes. Day of new information today. Then guys, next week there's an idea that's related that we're going to break into 2 days. We're going to relate what you learned today, which is polarity. We're going to relate that to a thing called intermolecular forces on Tuesday, and then we're going to relate that to the physical properties of substances on Thursday. So the next 3 days all sort of link together. And then guys, we're going to be in lab after Martin Luther King Day. Then on the 20th, we're going to wrap up that lab. Then on the 24th, we're going to be back in lab, and these are actually labs. And then guys, the 26th, we're going to talk about what we learned in Monday's lab, and then that next Friday, which is the last day in January for us, will be the test. Now guys, just looking ahead, I need to make you aware of this. This week down here where January turns into February, I'm actually taking my family down to Cabo San Lucas, Mexico. We need a break. And so, guys, that week down here where January turns into February, I'm going to be gone. Jesse's going to be, we're going to be gone. So we won't be here. You guys, not surprisingly, you'll see the days will still be productive. And actually, you're going to teach. I love that. So guys, Mr. Brown will actually be with you, so all the better. So he'll be working with you those days. But do you guys also know this, that we don't have school on this Friday? Did you guys know that? The school district, in all of their wisdom, this is not local level, this is the school board, in all of their wisdom decided that the only way to make our jobs harder is to randomize our schedule and just start shuffling days around. And so what they decided to do, not understanding that given how crazy school is, the best thing they could do for us is keep things consistent, especially given the fact that they jacked up Wednesdays. What they decided to do is just randomly make days in the spring days off. No idea why. They just said, hey, let's have days off. And as a student, you're going, yes. And as a teacher, as a person, I'm going, yes. As a teacher, I'm going, you guys are idiots. But that's what they decided to do. But then it gets worse because what they did, sorry, I'm ranting a little bit. It goes A day, B day, A day, B day. But then the problem is they didn't shuffle the rest of the calendar, making the next day a B day, so you have 2 A days in a row, and they just randomly sucked a B day out of the calendar. And then they did that again, and then they did that again. This happens twice in February, once in April, no idea why. But guys, February 4th, we don't have school, but I'm going to be in Mexico, so never mind. So, were you going to say something? Yeah, go ahead. No, but we don't get to give the school board credit for actually caring about that being important. I think they randomly didn't screw up the same days. They just started screwing stuff up, yeah. No. Oh, I hope not. Even if the answer is yes, let's go with no. At least in this class. So guys, Kimball's question was, are these going to be online learning days? The way the district has labeled them, they're labeled as teacher work days. I don't even know what that means. Was she raving too? Yeah, right. No, yeah. No, I think that's the one thing. Okay, so let's give them the benefit of the doubt. I think what they're trying to do, not successfully, but I think what they're trying to do is honor the fact that this year's been crazy, that teachers could use some space to just get things done. I don't know if you know this, but up in Canyon's district, every other Friday they don't have school. Did you guys know that? Yeah, up in Canyon's district, and this has been the case since like September, their school board looked at what's going on and they're just like, guys, these are manic, crazy days. Let's give everybody every 10th day off. And so every other Friday up there, they don't have school. But it's planned into the calendar, it's regular, it makes sense. I think that may be, David, what our school board was trying to do, only not well. But I think that's the spirit of this. It's just horribly implemented. So, yeah. I think we should grab Miss Shaw and have her have a guest appearance, and she could rant about this too. That'd be pretty good. Yeah, so anyway, guys, be looking for that. So, questions about the calendar? You guys okay? Are we good? All right. So, guys, grab your very favorite piece of paper and something you can write with. And, guys, here we go. So what we're going to do today is we're actually going to get into a concept that is going to be the foundation for our next 3 days. And this is what is called molecular polarity. I just realized, guys, I wonder if I should post this screencast after I just got done berating our school board publicly. All right. You know what? What's the worst they could do? Fire me. I'm going to leave it there. All right. Never mind. We're good. All right. So, I mean, they don't listen to us, and they certainly won't watch my screencast, so what does it matter? All right, so I'm being really snarky, aren't I? Never mind, it's a Friday. All right, so guys, molecular polarity. But did you notice when we did the test evaluation that we actually took time to look at the sections in the test? Guys, this is why. And I'll tell you when to start taking notes, but it's not going to be for a while. Guys, this whole idea of molecular polarity isn't new. What it is a reshuffling of a bunch of things that we've already talked about. We're going to start cherry picking all these ideas out of all these other places within the last month of what we've been doing together. And then, guys, we're going to tie it together in a neat little bundle, and you're going to get a lot of your homework done today. So let me show, again, don't write this down. Let me just show you how this goes. So guys, the first thing that we need to do is we need to come back to this. And we need to figure out what are the things from the previous unit that we're going to cherry pick. And the answer is this. Not salts and molecules, right? I told you that's in the next unit. But guys, we are going to cherry pick these three ideas. You've got to be able to draw Lewis dot structures. You've got to be able to figure out what they look like three-dimensionally. And then finally, you've got to be able to identify which elements are stronger around each one of these bonds. So guys, let's review that one really quickly just to make sure that we're super clear on this. So you ready? As you move to the right, do they get bigger or smaller? Smaller. Therefore, they get stronger or weaker? Stronger. So this way, stronger. Down, they get bigger and therefore weaker. Good. That's all you need to know in order to do this. Is that okay? All right. So guys, that's what we're going to pick out of the last unit. But then guys, in addition to that, we are going to start drawing, and you're not taking notes, guys, we're going to start drawing Lewis dot structures. But we don't need to know, we do need to know these. Guys, you don't need to know the names and angles. Did you notice that that was not an essential? Did you pick up on that? Guys, the names and angles are not essential. That's why we felt so comfortable giving you those cheat sheets for the test. Guys, you don't need to know the names and angles moving forward, so you don't need to worry about these anymore. So the names and angles, these things go away, but you do need to be able to draw Lewis dot structures. So that's thing number 2. Thing number 3 is this. Guys, remember in the lab when we talked about symmetry? You need to know it now, and we're going to talk about this. But guys, symmetry is going to also be critical to what we're doing. You guys understand that it just means the same all the way around, and we'll talk more about that. And then guys, finally, the last thing that we need to cherry pick is this. And you don't remember this at all, so we're going to go back over it. So guys, when you first learned about covalent bonding, you learned that there's polar covalent and non-polar covalent bonding. And along the way, you learned that if you have different nonmetals, these things share, but they don't share equally. And because the sharing is unequal, this creates things that are called dipoles, and this creates what are called polar molecules. So guys, again, I showed this to you a month ago, and I said, don't worry about it. We'll come back to it later. Well, guys, later is now, and we're going to come back to this. So again, here's what we're going to do. We're going to take Lewis dot structures, figuring out which atom is more electronegative, and then the symmetry stuff. We're going to grab a hold of this stuff. We're going to mush it all together. This is going to take us about 20 minutes, and then we're going to be done. You guys good to go? Okay. So guys, this then, I don't think the next slide is even stuff to write down. No. Okay, so this is don't write this down. So guys, this then is where we're headed with this stuff. These are our goals for today. So we're going to reconnect with Lewis dot structures, figure out what they look like three-dimensionally, an essential from the test. Then guys, after that, we're going to go over polar covalent bonds, which we did in the last unit, but we didn't even talk about. And then guys, finally, we're going to bring this together and figure out molecular polarities, and that's your goal for the day. You guys ready to go? Here we go. All right, so guys, first of all, this. I'm going to ask that you don't do this with me. You're going to have time to practice later. But guys, here's what we're going to do. We are going to come back to this idea of drawing Lewis dot structures, but now what we're going to do is we are going to draw them three-dimensionally accurately. And guys, let me show you what this means. For example, if I had you draw the Lewis dot structure of CCl4, can we all agree that it would look like that? And what is that shape? It's tetrahedral. And guys, even if we spent the time to build it, we would understand, I should have built these before, I forgot. Guys, we understand that this molecule actually looks like this. And so guys, this molecule is not flat, right? It doesn't have any 90-degree angles in it. What are those angles? You don't really need to know, but what are the angles? 109.5 degrees. And guys, this molecule actually looks like this. We understand that it's not flat, it's not 90 degrees, but this is as close as we can get to drawing tetrahedral, so that's how we're going to represent this. You good on that idea? Okay. So then, guys, let's do CO2. So guys, so this is tetrahedral. So then when we do something like CO2, guys, this is the Lewis dot structure for CO2. You've got a carbon. We did SiO2 on the test, but it's similar. So guys, we've got a carbon double bonded to an oxygen, double bonded to an oxygen, full octets, carbon dioxide. But guys, here's an interesting question. What is the molecular geometry for this molecule? And again, you don't need to memorize this, but because what is the molecular geometry of this thing? It's linear. Do you see that? Two domains, they're both bonding. Guys, this molecule is linear. Here's where we're going to make a little change in our thinking. So guys, this molecule is actually linear. Two domains, both bonding, it's linear. You don't need to be able to call this linear. But what you do need to be able to do is look at this and go, it's not bent. And if it's not bent, we are actually going to respect the fact that it's linear, and we are going to redraw it so it looks as much like as it actually is shaped. Does that make sense? So guys, if something's tetrahedral, we draw it like we saw a second ago. If something is linear, you don't need to be able to call it linear, but you need to understand that this thing is not going to be bent, and you're going to draw it linearly. Does that, okay. So guys, what about this then? Water. So guys, a water molecule, H2O, looks like this. You've got hydrogens and you've got oxygens. But now guys, let's talk. The domain geometry for this thing is tetrahedral. But what's the molecular geometry? It's bent. But guys, it doesn't look bent, does it? So again, what we're going to do is we're going to draw these as accurately as possible. We're going to understand that it's actually bent, and as a result, we're going to draw it. Again, it's not perfect, but we're going to draw it so it looks bent rather than linear. Does that make sense? Okay, so guys, what about this? NH3 looks like this. It's a trigonal pyramid. Guys, that's how we're going to draw a trigonal pyramid. It looks as much like this as it possibly can, so we're going to leave NH3 like that. HCl, this thing is straight. It looks like this. We're going to draw it as straight. But then, guys, what about this? CH2O. This was on the test. So, guys, if we look at CH2O, what's the domain in molecular geometry? Trigonal planar. And guys, we're going to draw this trigonal planar. And you've never done this before, although somebody did. Someone in here, oh no, it was in another class. So guys, this is how we're going to do this. We understand that it's trigonal planar, so we're going to draw a trigonal planar like that. We're going to try at some level to represent these 120 degree angles, and so we're going to draw a trigonal planar like that. So guys, does that sit okay? Now, the only thing that we're saying now is that when we draw Lewis dot structures, you don't need to know the names and angles by name, but you do need to try to draw the Lewis dot structures so they kind of look like what they really look like. Is that okay? You're all right on that idea? Okay. So guys, moving along then, the next thing that we need to remind ourselves about is this idea of polar covalent bonding. Don't write any of this down, but this is the idea. So guys, we understand that covalent bonding is sharing bonding, two nonmetals bonding together. But guys, polar covalent bonding happens when the nonmetals are different. And here's the way this goes. If the nonmetals are different, that means they don't have the same strengths. And if they don't have the same strengths, they still share, but they don't share equally. And this unequal sharing creates dipoles. So guys, a dipole is just the partial charge on a bond created by unequal sharing. So let me show you what this looks like. So guys, here we've got oxygen, here we've got fluorine. Grab your periodic tables. Looking at your periodic tables, which one is stronger? The oxygen or the fluorine? How do you know it's fluorine? Because nothing's stronger than fluorine, right? Guys, fluorine kicks everyone's butt. But remember, as we move to the right, they get stronger, so fluorine is stronger than oxygen. Now, guys, understand, fluorine is not strong enough to steal, but it just doesn't share equally. And here's what this looks like. Check this out. So this is the idea. So we get this electron being pulled in that direction because fluorine is trying to steal that electron, but oxygen is trying to steal that electron. But guys, look at where the electrons end up. Are they centered in the middle? Where are they at? Why are they closer to the fluorine? Because fluorine is stronger. Guys, this is why on the test we had you identify in atom pairs which one is stronger. Fluorine is stronger than oxygen. On the test, you just put one on the right, one on the left. But guys, fluorine is stronger than oxygen. That means that these electrons will be closer to the fluorine. Is that okay? Now, what does this look like? Well, guys, it goes like this. The fluorine closes in on the bond, and the oxygen closes in on the bond. But, guys, these electrons are closer to the fluorine because it's stronger. This is what happens. Guys, when we actually talk about the structure of this bond, it turns out that this side is slightly negative. Remember, the electrons are negative, right? And they're closer to this side. So this side is slightly negative, and the other side is slightly positive. And we call those dipoles. So guys, the stronger atom pulls the electrons over. This side is negative, slightly negative. We call it the negative dipole. This side is slightly positive. We call it the positive dipole. But guys, here's how we represent this. What we actually do is draw an arrow. This is something you're going to be doing today. Guys, we actually draw an arrow. And what does the arrow represent? The arrow represents the direction the electrons travel. Now, guys, why are the electrons moving to the fluorine? Stronger. And so literally this arrow just represents the direction the electrons travel. But guys, watch right here. Watch my finger. Here's what we do. We actually cross this end of the arrow. So that means this end is positive and the electrons are moving in that direction. Questions on that? Guys, we're almost done. You guys good on that idea? Drawing arrows, you understand the arrow points at the strongest atom, and that's the direction the electrons flow. Is that okay? All right. So guys, this is then what we're going to do with this today. You are now going to take all these ideas. Think about what we talked about. Drawing Lewis dot structures as three-dimensionally accurate as possible. Then figuring out the direction the electrons flow based upon their strengths, their electronegativities. Guys, we're going to bring all of those ideas together, and this is where you're going to start taking notes. Guys, we are now going to learn to identify, we are now going to learn to identify molecular polarities. Guys, write this stuff down. This you need to know. So how do you do this? Well, guys, these are the steps. We like steps. So in order to do this, the steps go like this. Step number one is draw the Lewis dot molecular structure as realistically as possible. Just talked about that. Am I going too fast? Okay. Step number two, draw the polarity arrows for each one of the bonds. But we just showed how to do that. Figure out which one's more electronegative, draw the arrow. Then guys, step number three, determine if the molecule is polar. Because while you're writing this down, remind me if I forget. I want to talk with you about, ready for this? I want to talk with you about your papers that you wrote, your nuclear chem papers. Don't let us wrap up the day today without talking about those. Okay, so how do we figure out if the molecule's polar? And guys, This is all about symmetry. This is why we talked about symmetry in the lab. This is why we said we're coming back to it now. It's all about symmetry. So here's how this goes. If the molecule is balanced or symmetrical, it is nonpolar. And what you're going to do is you're going to label the molecule nonpolar. Now, what if the molecule is not symmetrical or imbalanced? Then, guys, the molecule is polar. And you're going to represent that by drawing a polarity arrow in the direction that the electrons are moving. And guys, when we say that, we don't mean the electrons for one of the bonds. We mean the electrons for the entire molecule. Guys, that's it. You're now done taking notes. What we're going to do is we're going to look at 4 or 5 examples, and then I'm going to talk with you about your papers, and then we're going to get some homework done. But guys, as you're getting ready to look at these examples, guys, some of you are going to find these, I think, interesting and fun. Typically, my students go, oh, this is kind of cool. If, however, you get into these and you're like, oh my gosh, last unit sort of crumpled a little bit. I'm not comfortable drawing Lewis dot structures. I don't understand the structures. I don't get the 3D stuff, whatever that may be. Guys, understand that you're not going to have a lot of time to practice. And remediation is possible. So if you're in that spot, I know that the essentials test isn't for almost 2 weeks. Guys, do the remediation now. Because the remediation is teaching you all the stuff that you need to know to do this. So guys, if you find that you're stuck on this, the very best thing you could do is go home tonight and watch the essentials video. You want to get on this quick because you know that all of this is foundational. So, you guys ready to go? Let's look at some examples. So, guys, these I would encourage you to do with me. But these are now the same molecules that we did before. So, guys, quickly, if you would, scratch CCl4 into your notes. Make them big, like maybe, what, 1.5 inches or 2 inches across? 4 or 5 centimeters? Not that you guys think in centimeters, but... You guys do, of course, know that we're the only first world country on the planet that doesn't use the metric system. Yeah, not a source of pride. Did you guys actually know, though, that as a country, we're actually technically on the metric system? That we signed the metric compact in 1972, and we are actually on the metric system. But what we do is we actually take all of our units and convert from metric into English, but technically the entire country's on the metric system. We're a mess. Anyway, all right. So, guys, this is what we're going to do to figure these out. So step number 1, draw the Lewis dot structure as accurately as possible. This is tetrahedral. This is as close as we're going to get to tetrahedral. Now, guys, do this. We are now, step 2, going to draw in the polarities for each of the bonds. So, looking at the periodic table, which element is more electronegative, chlorine or carbon? Kind of weird, right? Because, guys, if you look, you'll notice that chlorine is to the right, making it stronger, but chlorine is also down, making it weaker. So what do we have to do to make sure? Flip it over on the back and look up the numbers. Guys, carbon is what, 2.55? And chlorine is like 3.1-ish? Is that right? My brain is full of worthless information. So, guys, chlorine is stronger than carbon. Do this with me. Here's what you're going to do with that information. Chlorine is stronger than carbon. So, guys, what we're going to do is we are going to draw an arrow towards the chlorine. Because the chlorine is pulling those electrons, and then cross this end because that end's positive. But, guys, that's happening here as well, and it's happening here as well, and it's happening here as well. And literally, guys, this carbon atom is being stretched in all 4 directions by these chlorines. Does that make sense? Now, guys, here's the interesting bit. We now need to figure out what this does to the entire molecule. So now we ask ourselves this question: is this symmetrical? Yeah. And guys, because it's symmetrical, what that means is all 4 of these poles cancel each other out. If you've taken physics, these are called vector sums. Do you remember in physics where you learned to draw vectors, and the longer the vector was, the stronger the pole was? Well, guys, these poles are all the same strength, but because they all offset each other, all the poles cancel, and that makes the molecule nonpolar. So because it's symmetrical, it's nonpolar. So guys, I hope right now in your mind you're asking yourself this question: who cares? Well, guys, the answer is I do, because that means that this is a gas. Guys, every single molecule that you know to be a gas, the oxygen that you breathe, the nitrogen that they now put in your tires at Costco, the hydrogen in balloons, guys, every single thing that you know to be a gas is symmetrical. Because symmetrical molecules are not sticky, and that turns them into gases. So guys, this molecule is a gas. Do you get the idea? Okay. Now, guys, I've got to sort of punt for a second, and let me show you why. Last night, I animated all of these arrows. Look at me go, right? So I animated all of these arrows, but frankly, I don't want to do that this way. I think it's better if I just draw them. So I'm going to hide the animated slide. Actually, here, I'll just do this. Let me unskip this and then come back to the slide that I didn't animate, and then we're good. Okay, so guys, here we go. Carbon dioxide, scratch it in your notes. CO2. And if you're really feeling brave, draw in the arrows. Oh, yeah. That's what I was doing last night, Jesse, while I was waiting for you to get home from volleyball practice. I was animating arrows in my lecture slides. Yeah, that's kind of how lonely my life is right now. What? No. Yeah. Again, that's how sad my life is. You guys got the Lewis dot structure? Did any of you bravely draw the arrows? Guys, which one's stronger, oxygen or carbon? Yeah, and this one's straight off the trends, right? Oxygen is to the right of carbon, so oxygen is stronger. And guys, what that means is this bond is polar in that direction, and this bond is polar in that direction. And guys, oh, that's not it. There it is. So guys, carbon dioxide looks like this, and literally what that means is this bond is stretched in that direction, and this bond is stretched in this direction, but is it symmetrical? Yes. Therefore, the poles cancel out. Therefore, carbon dioxide, wait for it, is a gas. What do you know? You already knew that. Guys, it's a greenhouse gas. It's killing all of us, but this is non-polar because it's symmetrical, and as a result, it's a gas, and as a result, it goes up into our atmosphere and traps heat. It makes the world get warmer. Yeah.
Dry ice,
yeah, interesting, right? So here's the thing that's tricky. When we say that this and this are gases, we mean at room temperature and room pressure. Okay? Understand that any gas can be liquefied. For example, I'm going to throw this to you. So inside that can, it's a duster, but shake it gently. Shake it. Yeah, turn it on its side and shake it. What's in there? A liquid. That's actually liquid air. So here, give it back to me. So So what is air made of? And the answer is air is made of 70% nitrogen, about 28% oxygen, and then some trace gases. But nitrogen and oxygen are both nonpolar, therefore they're gases. But they can be liquefied, and the way that we do it is we put it under hundreds and hundreds of pounds of pressure. And when we do, it shoves the molecules so close together that we force them to stick and turn into a liquid. But the minute you take the pressure off, it turns back into a gas. So these molecules will be a gas at this condition, standard temperature and pressure. We've got to compress them, high pressure, to get them to stick together. So when we say nonpolar things are gases, we mean at these conditions, not these conditions. Does that make sense? All right, so guys, how are we doing on CO2? You guys good? Okay, so now let's do this one, but please don't write this down until you see it. So guys, water, right? No. Why ain't that water? Because water's bent. How are you supposed to know? Because somewhere in the back of your brain you should realize that 4 domains, whether you know the name or not, is tetrahedral, but 2 bonding domains is bent. And so guys, what we're going to do is we're going to redraw this thing as bent, and it looks like this. So please draw water, but draw water bent. Then guys, again, if you're feeling brave, please draw in the arrows. So which direction, which one is stronger, oxygen or hydrogen? The oxygen. So guys, this bond is polar towards the oxygen, and this bond is polar towards the oxygen. Now, is the molecule polar? Ask yourself this question. Is this symmetrical? It is not symmetrical. Guys, if you look at the molecule, you can see clearly that it's not symmetrical. So what do we do with this? Guys, you do this mentally. I'm going to do it physically. Watch. Which direction is this bond going? To the left. Which direction is this bond going? Up. So what happens when you bring left and up together? You end up with left up. And left up would be that, and that is the overall polarity of the molecule. But now we've got, ready? This is life-changing stuff, guys. This molecule is polar. Therefore, it's sticky. Therefore, it sticks to other water molecules. Ready? That means water's a liquid, huh? You just learned why water's a liquid. Guys, water is a liquid because every single one of these water molecules is bent and therefore polar, and that makes them like little magnets, and that makes them stick together, and that's why water is a liquid. You just learned something. So, you guys good on that idea of left and up? You scratching or, yeah, you guys good? Okay, so guys, let's finish this up, and let's talk about your papers, and then let's go. So, NH3. Which is stronger, the nitrogen or the hydrogen? Nitrogen. So guys, this bond goes this way, this bond goes this way, this bond goes that way. Now, is it symmetrical? No. So what is the sum of in and up? Up. The overall flow is up, and that makes this polar. Therefore, it's sticky. Therefore, it's a liquid, but you already knew that because this is ammonia, the stuff that you clean your bathroom with. Okay. All right. So, guys, continuing on, we're going to do a couple more. HCl. And then one more to go, and then we're going to talk papers, and then you're going to work on homework. Which is stronger, hydrogen or chlorine? Chlorine. So the bond goes this direction. But guys, that is also the polarity of the molecule, because the molecule only has one bond. That got easy. So now guys, let's look at the last one. To me, the most interesting one. CH2O. Notice that we are now drawing this thing as close to trigonal planar as we possibly can. And then we need to draw in the arrows. So guys, check me on this. Carbon is stronger than hydrogen and oxygen is stronger than carbon. Is that right? Is that, yeah? You're not just agreeing because I'm not confident. Is that, okay. So carbon is stronger than hydrogen. Carbon is stronger than hydrogen. And oxygen, did I do that right? Oxygen stronger than carbon? I think I did that right. Okay. So guys, is this symmetrical? Clearly no. So what direction is the flow? We've got here and here and here. Guys, what direction is this entire thing flowing? To the right. So we're going to do it like this to the right. By the way, guys, what you're going to see in the homework is sometimes I'll draw the arrow down below the molecule. The reason is because when I draw the arrows through the molecules, sometimes it covers up the bonds, and it's nice to be able to see that that's a double bond. So if the arrow's down below, don't let it freak you out. I'm just trying to not muddle the molecule. But, so guys, if this is polar, is it a gas? If this is polar, is it a gas? No, it's a liquid. But guys, I think some of you already know that this is a liquid because this compound is actually formaldehyde. This is the stuff that biology teachers soak dead stuff in so they don't rot. Have you ever been in biology and looked at the back and there's all the dead stuff in jars? Guys, all those jars are actually full of this stuff. It's called formaldehyde, and it's a liquid that keeps things from rotting. So there you go. Guys, questions on what we're going to... This is your homework today. Anything you need to talk about? Okay. So guys, let me do this, and then I'll give you your homework. Guys, I want to come back to these papers that you wrote. I need to be careful about how I do this. So let's just talk. So guys, I think you knew from the start that these papers that you wrote were at some level experimental. We had never done this. Miss Call and I had never done this before. It's something that we always wanted to do, but just never did for a number of reasons. And finally, in working with Mr. Ellingford and other English teachers, we felt like we could do this and do this successfully. And guys, you know Miss Call and I well enough to know that if we're going to do something, we're going to do it well. Guys, we kind of feel like we failed you, to be honest with you. This did not go as well as we wanted it to. There were so many variables, so many things that were out of our control. It didn't turn out the way we wanted. With that said, though, guys, we still believe the experience was valuable. Because the reality of it is when you get to college, you're going to have professors in every single one of your classes, not just English, in every single one of your classes that are going to come to you and say, hey, you're going to write a paper and here's what it's about. In college, papers and presentations are the way that you communicate. So we still believe fully that it was worth you writing a paper in a chemistry class. We just don't feel like it went as well. It wasn't as high quality of an experience as we're accustomed to developing. And so guys, the bottom line is we don't want to punish you because we did well. The system was just broken. And we don't want to punish you for that. So here's what we're going to do. This is the best way to explain it. So, guys, this is 0 points. This is 30 points. Your papers were worth 30 points. So, guys, here's what we're going to do. So this is 10. This is 20. So, guys, what we're going to do is we are going to create what we're thinking of as being grade buckets. And what we're going to do is we are going to round up in these grade buckets. So guys, if you were above 20. So if you were 21 or up, we're going to round your score up to 30. You're going to get a perfect score on your paper. Okay? If you were 11 or above, we're going to round your score up to 20. If you were down here, we're going to round your score up to 10. So the scores that you can get on these papers are 10, 20, and 30. Now you're thinking to yourself, wait a second, I'd really like to get a 30, but I was down in the 10s and 20s. We're going to make an allowance for that. So guys, here's what we're going to do. If you don't like your score on your paper, you may still rewrite it. And when you rewrite it, we are not going to send it to the BYU graders. Miss Call and I are going to score it. And we will then give you, hopefully, that better score on your paper, still respecting the grade bucket rounding that we're talking about. The only difference is this. The cap will become 27. Because there's a 10-point deduction for rewriting or only turning it in late, the best you can get then is 27. So if you land in this zone on your rewrite, you'll get 27. If you land in this zone, you'll get 20. Still, if you land in that zone, you'll get 10. No, that's not true. Did we go? No, we went 3 points off of all of them, didn't we? Okay, sorry. So this would be 17 and this would be 7. So there is a 10% deduction in each of those. But if you'd like to rewrite your papers, you're welcome to do that. Guys, with that said, your rewrites are due. How do I get? I can't do it from there. Sorry. Guys, your rewrites are due. It's on the calendar. Maybe some of you noticed it as we were looking. Oh yeah, down here. So guys, your nuclear paper rewrites are due on the 21st. Anytime before that, but they're due on the 21st. If you want to go to the Writing Fellows to get more support, you're welcome to do that. Go to your English teachers if you'd like. But guys, if you want to rewrite your papers, those will be due the 21st. And I'll put scores in hopefully later today. So guys, the bottom line is this. Thank you for investing in this process with us. Miss Call and I are always learning. We're always trying to do things better. But we finally realized that this is something that just became, well, it wasn't what we had hoped. And so we want you to understand it was a good experience, but the details got muddled, and we don't want to hold you guys responsible for that muddling. So that's what we're going to do with your scores. So questions about that? You guys okay? Okay. All right, so guys, here's the homework. You got about 15 minutes left. Let me get these to you. I want to talk to you about them for a minute, and then we're going to get going. Did I not pick up your tasks? Oh my gosh. Here, I'll get them while you're working on homework. I looked down and it's like, oh gosh, those are still there. So guys, as you know, this is the homework packet for the entire unit. Okay. So guys, look this over with me. So there are 14 Lewis dot structures that you're going to draw. But notice the instructions of obviously another sheet of paper. It says draw the Lewis dot structures as three-dimensionally accurate as possible. Then draw the polarity arrows for the bonds. And then indicate the polarity of the molecule by drawing the bigger arrow or indicate that it's nonpolar. So you're going to do that. But then, guys, I know that down below there's 6 more questions. Guys, we're going to answer those. But if I may, pay special attention to question 19. We are going to spend a fair amount of time on question number 19 when we grade homework on Tuesday. Guys, the answer to question 19 is interesting, but also important. So spend the time that it takes to answer. I would encourage you to not look at the answer until you've tried to answer it. All the answers are posted on our website. But spend some time on 19. But guys, understand you can't do 19 until you've done 1 through 14. You need to draw the Lewis dot structures first. All right, so guys, 10 minutes. I'm going to come around and pick up these, your tests and stuff as soon as I stop recording. And let's get as much of this done as we possibly can.